Right. Yesterday we worked with average rate change of functions. A little bit of review from what we did in pre-calc. We did this in pre-calc. Once again, rate change. We have some function f of x to find our rate change. As we talked about before, the rate change is basically if I drew a secant line between 2 points of x and y and find the slope of that secant line, and that's my rate change. So I have some function, I have some interval of a to b that I want to find the rate change. Rate change. It just basically turns into our slope formula, delta y over delta x. We talk about velocity, average velocity. We can also deal with the displacement time graph. We just change our function rather than f of x. We change this to displacement. We can have d of x. We can have s of x as a displacement, or d at t and s at t because we're dealing with time there. And we can find our average rate change of d at a or b minus d at a over b minus a. Once again, we're not dealing with the time intervals. You had four problems to do on four problems to do. Page 82, questions you have. It's a matter of plugging into a function, find your function values, and subtract your y values. Subtract your 2y, subtract your 2x's. All right, we will need our calculator today. A lot of clickety-clacking through our calculator today. We start working with the idea of the basis of calculus, the basic elements of calculus, and that's the idea of limits. Okay, the idea of limits. Limits that we will utilize will forward into everything we do calculus-wise from here on out. There will be a fingerprint of limits and everything else we do throughout the rest of the year. So we have to look at the idea of limits. When we look at the idea of limits, as the value from the domain is approached, the range approaches a value, this is called the limit. As the value from the domain is approached, the range approaches the value. This is called the limit. And we can, I don't want to say dummy it down, but we can water this down or put it back into our brain's ideas. As x gets closer to a value, what does y get closer to? As x approaches a value, what does y get closer to? You can think of this as open dots. If I said x is greater than 2 and I was going to graph x is greater than 2, what would we put at 2? An open dot. And we go to the right. Okay? If we take a look at this, what's my x value? That is my smallest x value that I right next to the value 2. Well, we can say it's 2.1, but then we can say it's 2.01, then we can say it's 2.0001, and 2.00001. We can get closer and closer and closer to this 2. That's what we're dealing with here. We're getting closer to a value. We're getting that open dot away from a specific value. Okay, what's that open dot away? F of x is equal to x plus 2. What does f of x get closer to as x gets closer to 1? Okay, as x gets closer and closer and closer to 1. Well, I'm looking at 1 point, or 1. I don't want to use 1, but I want 1.01, 1.0000001, 1.0000001. Well, if I'm plugging in values getting closer to 1, what does f of x get closer to? What did you say it was? 3. So my limit as x gets closer to 1, my value, my limit gets about closer to 3. Well, how do we write this nomenclature? How do we write this? Well, we start this out with the limit and abbreviate the limit to LIM. X is getting closer to 1. So underneath our limit, we write our x value. We put an arrow and a 1. How this is read is the limit as x approaches 1. This is the limit as x approaches 1. Well, we have to also declare what function we're dealing with. Well, we have our function f of x, or we could say the limit as x approaches 1 of x plus 2. We have to have a function or a rule that is there. So this is how things are written with respect to limits. Well, let's take a look at some calculations here. This is where we're going to use our function. What I would suggest you do in your y1, this will make life a little bit easier. In your y1, type in your 5x minus 3. And then calculate your value at 0.5, at 0.75, at 0.9, at 0.99. What we are doing is we're approaching the value 1. We're getting closer and closer and closer to this value of 1. So, Justin, if I read down my values, what do you have? What do you have?
Negative 0.05, 0.75, 1.5, and then 1.95.
What if we had 0.9999? What if we threw 0.999 in there? What would we get? 1.995. What if I had another 9 in there? 1.995. 5. What are we getting closer to?
2.
Okay, we're getting closer to the value of 2. So my limit up here is the value of 2. Well, what if I had the limit as x approaches 2 of 5 minus 2x? So in my y1, I'm going to type in my 5 minus 2x. And then find your value at 1.5, 1.75, 1.9, 1.99. We're getting closer and closer to the value of 2. find the other one. Throw another in there. Jacob, what do you have? Write down your values.
2, 1.5, 1.2, 1.02, and 1.002.
What are we getting closer to?
1.
Getting closer to the value of 1. Well, when dealing with limits, this is a fundamental way, the very fundamental way of calculating a limit. If you're sitting, you go to college and they want you to take a math placement test, and all of a sudden limits get thrown on there. All the rules that we will talk about with respect to limits, you may or may not remember. But what you can remember is what is a fundamental idea of limits. As x gets closer to value, what's y get closer to? So what you could do is if you have the limit of a function, you can ultimately just type in the function and just calculate values as you get closer to this value. And you can come up with a limit. Because, yes, there's easier ways of dealing with it. But do we remember or not remember? What's easy to remember is hopefully the basic fundamental idea of limit. I'm pulling in values of x. I'm seeing as I get closer to value, what does y get closer and closer to? So we have here is we started out with our first limit. Limit as x approaches 1 of x plus 2. And we came down to a value of 3. We could put in 1 point or 0.5, 0.75, 0.9, 0.999, 0.99999, and we get closer to the value of 3. But what's an easier way of dealing with limits, the idea of limits? Well, we have a substitution principle. The limit as x approaches a of f of x. We could just substitute in the value of a into our function. So up here, I can say we can go with 5 times 1 minus 3. We get 5 minus 3, which is a value of 2. Over here, we could go 5 minus 2 times a value of 2. 5 minus 4 is a value of 1. Now, what is understood when dealing with limits? This is sort of, once again, going back to our definition. We are approaching a value. We're getting closer to value. When you calculate limits, we put an equal sign in there. But what you'll also see in books as you go along is you also will see an error there rather than an equal sign, which tells us as x approaches 2, this approaches 1. As this gets closer to, this gets closer to 1. As this gets closer to 1, this gets closer to 2. As this gets closer to 1, this gets closer to the value of 3. So that is another way of writing, and you'll see that sometimes in calculus books. They'll have arrows here rather than equals. But if you look at the fundamental definition of limit, when we're calculating limits and we're saying the limit is equal to this, the approaching is understood. Even though I'm saying it's equaling that, I'm really just approaching that. But one way of finding what we approach is just plug it in, plug it in. Plug it in, plug it in. Plug it in, plug it in. Okay, so that's one way of dealing with limits. Discontinuity. When you talk about discontinuity, we've dealt with these before, but I don't know if we call it discontinuity. But another term here. What we basically said was, here's a function. When we look at the idea of discontinuities, what we've looked at before is the domain. If I give you this function, if I give you this function, f of x equals x plus 3 over x plus 4, what's your domain? Negative, positive infinity. What do we exclude? X cannot equal -4. Well, when we talk about a discontinuity, it's the value from the domain that makes the function undefined. It's basically, what do we have to exclude? Well, what we have to exclude is we have to exclude x equals -4. So the value that makes our function undefined gives us what we call a discontinuity. X equals -4. It is your exclusion values when you look at the domain. What do I have to exclude? So if I look at my second one, what values would we have to exclude in the second one?
-6 and 1.
-6 and 1. Okay, the bottom, x squared plus 5x minus 6 equal to 0. We could factor this to x and x. We would have plus 6 and minus 1. So x, you said, is -6 and positive 1. So we have discontinuities at -6 and positive 1. Okay, those are discontinuities. It's again a new term that we utilize. Well, let's go to the back here. Let's look at some limits. We have the limit as x approaches 5 of x squared minus 25 over x minus 5. And we want to calculate a limit. Well, if we look at our principle, how we can calculate a limit, the substitution principle, it tells us we just sub it in, sub it in. Plug it in, plug it in. Plug it in, plug it in. Well, if I plug it in, we have 5 squared minus 25 over 5 minus 5. So we have 25 minus 25 over 5 minus 5. We have 0 over 0. So if I would take 0 and divide it by 0, will I get a value? No, Houston, we have problems. So the substitution principle lets us down. So we now take a look at go back to our fundamental idea. When all else fails, type in your function into your y1. Quantity, make sure you quantify the numerator and denominator. Quantity x squared minus 25 over quantity x minus 5. Make sure you quantify both numerator and denominator. Now what we want to do is we want to plug in values that get us closer and closer and closer to 5. 4.75. F at 4.75. F at 4.9. F at 4.99. F at 4.999. And we can do values that way. We can find our values. Well, if we do that, once again, this goes back to our fundamental ideas and definition of limits. What do we get closer to? 4.75, 4.9, 4.99, 4.99, and we get closer and closer to the value of 10. This gives us 9.75. This gives us 9.9. This gives us 9.99. This gives us 9.999. So we get closer to the value of 10. But going back and utilizing our calculator can be very cumbersome. So how else can we look at this idea? Well, let's go back to square one. Limit as x approaches 5 of x squared minus 25 over x minus 5. If we take a look at our function, x squared minus 25 over x minus 5, where would our discontinuity be? 5. Okay, so we have a problem because we're approaching a discontinuity problem, which if we go back to what is the discontinuity? Well, the discontinuity is the value from the domain that we have to eliminate, that we can't equal. Well, we're trying to find the limit as we get closer to that. So there's issues with that. But if we take a look at our numerator, x squared minus 25, what could we factor that down to? Difference of perfect squares. X minus 5 and we can factor that down to x minus 5 and x plus 5. Well, if I take a look, I have a common factor of x minus 5. They cancel out. So what this gets reduced down to within our limit is the limit as x approaches the value of 5 of x plus 5. Now if we plug it in, we get 5 plus 5. Which gives us our 10. Once again, we're getting closer and closer to 5. We're never achieving it. Our y value is getting closer and closer and closer to 10. But we'll never achieve that. We get 9.99999. So if I look graphically, what do you think appears on our graph? I get closer and closer to x equals 5, but I never achieve it. What happens on our graph there? No. As x gets closer to 2, x is greater than 2, we can never achieve it. What do we put on our graph? Open dot. We're going to get an open dot. We're going to get closer and closer to 5. Where would be the open dot? X would be 5. What is y getting closer and closer to? Do we ever achieve it? No. We get closer to 5, we get closer to 10, we never achieve it. So what we get is we get an open dot at the ordered pair, x is 5, y is 10. What this process is called removing the discontinuity. We have removed the discontinuity and be able to calculate our limits. When we're removing a discontinuity, okay, as we're trying to do limits, we try to plug it in. Does it work? If it doesn't work, then we try to factor, cancel, and then sub. That's removing the discontinuity. Well, if I take a look at my next one here, I got a limit as x approaches 4 of x squared minus 16 over x squared minus 3x minus 4. First thing we try, plug it in. 4 squared minus 16 over 4 squared minus 3 times 4 minus 4. On top, we get 16 minus 16. On the bottom, we get 16 minus 12 minus 4. We get 0 over 0. So if that doesn't work, we look to factor, cancel, sub. So factor your top, factor your bottom. Make sure you trace your limit along. You drag that along. We can't just change a function by itself, but we can change the function with inside the limits. So you need to continue to drag along this limit as x approaches 4. So drag along your limits with that. So we have a limit of x approaches 4. Top is once again difference of perfect squares. X plus 4, x minus 4. Bottom factors of what? So we factor, we look to cancel, and then we can sub. So on top we have 4 plus 4 over 4 plus 1. So we factor, we cancel, and then we sub. So we have 8 over 5. So as x gets closer to 4, y gets closer to 1 3/5, or 1.6. Once again, that would give us this open dot idea. We have an open dot at the ordered pair x is 4, y is 8/5. We'll worry about the graphing a little bit later as we advance on. I'm throwing it at you right now just to give you a flavor of meaning behind approaching. When you're approaching, you're that open dot away from the exact point. Well, let's try the next one. We plug it in, we get 5 plus 3 over 5 minus 5, or we get 8 over 0. Well, if I click and clack 8 divided by 0 on my calculator, we get a domain error because we cannot divide by 0. Once again, if I looked at my domain here would be x, remember, positive, negative infinity, x cannot equal 5, which would be a discontinuity because we have to eliminate it. Well, our first step of eliminating it would be removing discontinuity, factor, cancel, and then sub. Can I just cancel out my 2 x's there? I have x's out in front, both of them. I have x plus 3 and x minus 5. Can I just scribble them out? No, we can't. If we had multiplication there, if I had 3x over 5x, I could cancel out the x's. But with the addition in there, if I take the value of x and add 3 to it and the value of x and subtract 5, I'm not going to get the same value as just 3 over x. So what happens now? I can't factor, cancel, sub. Well, let's go back to see what happens in our calculator. In our calculator, type in the quantities. And it's approached the value of 5 at 4.9, 4.99, 4.9999, 4.9999. what's happening to our y value. Gets smaller. Goes towards negative infinity. What if I had what if I got closer to 5 on the other side? 5.1, 5.01, 5.001? What happens to our y value now? Goes positive infinity. I get bigger, really big, or I get really small. So our solution comes down to, and right now we don't have enough in our arsenal to be able to define exactly what it's going to be. We can just say it's positive or negative infinity.
It's got major each other.
Well, what if I put in 0? I get square root of 4 minus 2 over 0. And we have a problem again. Well, now I really can't factor. I get 0 over 0. So what other things do we have up our sleeve to be able to solve this? Well, we can solve this by looking at the idea of a conjugate. We can multiply numerator and denominator to make an equivalent fraction by the exact same thing. But we want to take a look at its conjugate. What's the conjugate of the square root of h plus 4 minus 2? What's the conjugate of that?
Square root of h plus 4 plus 2.
There we go. So if we FOIL out the top, we get square root of h plus 4 times square root of h plus 4, which gives us h plus 4. We get a plus 2 square root of h plus 4. We get a minus 2 square root of h plus 4. Then we have a minus 4. On the bottom, just leave it as a factored form. Now on top, these two things cancel out. Then I have h plus 4 minus 4, which also cancels out. So what we're left with is limit, once again, drag your limit along, h approaches 0 of h over h times square root of h plus 4 plus 2. So if I put in my 0 for h, I just get zeros. But I can now cancel those. You give us 1 on top. Now if I put 0 in for h, we're left with 1 over square root of 4 plus 2. Because 0 plus 4 is 4. So we have 1 over 2 plus 2. So we get 1/4.
Can h not equal negative?
Hmm?
Oh, wait.
H would equal 0 would give us a discontinuity again, because we would put 0 at the bottom. All right, limits, the idea of limits. It's something that's new. This is new. Once again, this is the basis of everything that we utilize going forward in calculus. For homework on the weekend, 102, 103, 1 to 31, the odds. There's just a bunch of limits to do. Monday, I will not be here, but you'll have a worksheet that deals with the idea of limits again. Once again, that's why I want to forge through today, so Monday you have something to do. All right, questions?
Do you think limits is hard? Or just a lot of stuff?
It's just new. Think about